All right, hello Precalculus students. This week is week 8. Last week we talked about limits and specifically special types of limits called derivatives. And we wouldn't have normally called them or talked about derivatives as early as we did, but I did so because we won't have time to formally go into derivatives. So I kind of gave you a sneak peek there of derivatives last week, and hopefully you found that at least interesting, if anything else. I mean, it was challenging, I think you would agree. But this week is going to be kind of a slightly different tone, and I think it's also perhaps maybe easier than what we were doing last week. We're talking about continuity, and the layman's definition, or perhaps the easiest to understand definition, is this one here that's usually given up top. If you can draw a graph without lifting your pencil, then we would say that that function's continuous. No breaks, holes, gaps, or anything like that, or asymptotes. So here, if we were to draw a continuous function, that looks to me to be a continuous function. But the moment you have to pick up your pencil and continue, then there's a gap or a break in the function. So that would not be continuous. So that's kind of the easy definition, but in calculus, that's really not good enough for us. We can't just have something, a definition so subjective as you can't lift your pencil. So this right here is the formal definition. This this content down here. So let's go ahead and read it. It says to be continuous at a value c, this is an x value, all of the following criteria must be met. If not, the function is said to be discontinuous at c. So let's see, you must show each of the 3 criteria to justify discontinuity. You must show that, so to show a discontinuity, you have to show that one of these 3 is false. So I'm going to kind of highlight them. So I could say 1, 2, and 3, or I'm just going to say blue, green, and red. There are 3 conditions. Let's look at them one at a time. This first condition is pretty straightforward. F is defined at x equals c. F of c must exist. So you can't have something like this. Say c is 0 and then it's 1 over 0. This is undefined. So you can't have something like that where you plug in 0 and it gives you a 0 in the denominator, or perhaps you have something like this where you have a piecewise function. You have maybe x when x is greater than 2, and then x minus 1 when x is in between, say, I don't know, greater than 2. So this is going to be 1 to 2, including 2. So, and if I were to try to plug in something like 0, it's undefined. It doesn't go to either one of our rules here. 0 is not greater than 2, and 0 is not in between 1 and 2. So this 0 would be undefined. So the first rule, or the first condition that must be met, is that the function simply must be defined. If it's not defined, then there's no hope of continuity at the point. Next condition is the limit must exist. Now, to break this down further, we know in order for a 2-sided limit, this is 2-sided, in order for a 2-sided limit to exist, you have to have the left limit, so the limit as x goes to c from the left of our function is equal to the limit as x goes to c from the right of the function. So the left-hand and right-hand limits must be equal. So another way that this is usually stated is they both must exist. So let me maybe write this a little bit more formally. Put a comma in between these. We'll say exist, which means that the limit goes to a specific value, a number, and are equal. So the limits exist and are equal. Furthermore, so the very last condition, not only is the function defined, so f of c is defined, is the first one, and the second one is the left-hand and right-hand limits are equal. They exist and are equal, so the 2-sided limit exists. But the third one is they all are equal, so f of c equals the 1-sided limits. So this is sometimes called the continuity statement. When I first started teaching I started teaching calculus at Ohio State University, and they had kind of like a training session where all of the graduate students would teach a course or teach a sample class to all the other graduate students. So it was kind of like teacher training, and it was a lot of it was just kind of on the fly, so it was kind of high stress. And I came up and they asked me, they said, okay, teach us some material on what it means for a function to be continuous. And so I immediately just wrote this on the board. Okay, that's what it means to be continuous. And they said, yeah, but what else? Is there anything else that's required to be continuous? And I said, well, the function has to be equal to the limit. That's what it means to be continuous. And what they were looking for, what I didn't realize they wanted, is they wanted me to really expound a little bit more. They said, hey, they wanted the function to be defined, and then the limit has to exist. Not only is it defined and it exists, but they want it to be equal. So I managed to biff that up my first year teaching, but I have since learned from it. So here we go. So the next is the types of discontinuity. We'll really see two types here, and we put them into two categories called removable and essential. Removable, there's really only one subtype underneath removable. It's called point. At least one subtype that we will talk about. And essential discontinuity, there are two types, either a gap, or I would prefer to call this one infinite. So you could call it asymptotic discontinuity, but I feel infinite is what most textbooks use. At least that's what I've seen. So let's go ahead and jump into some examples. So we'll keep these types of discontinuity in mind, but let's go ahead and jump here. It says, where is the graph discontinuous? So I see multiple locations where the graph is discontinuous. Let's go ahead and list them. The first location is right here at -3. You can see that there's a hole. So we'll say x = 3. Now, when they say where, they're looking for an x value. Not an ordered pair, but an x value. So where else? Here at 2. Whoops, I think I meant -3 perhaps here. And then this one is a +2. And then this one right here, where there's a gap between the two values, that would be x = 3. So we have 3 locations of discontinuity. Part 2 says, why is it discontinuous at each of those values? Name the type of discontinuity for each x value. Okay, let's take them all one at a time, one in each in turn. So we'll say x = -3. Why is it discontinuous here? Well, I think if we were to follow our conditions, let me maybe write them on the side. One is f of c is defined. The one that I did in green was 2. The limit exists, so the limit as x goes to c of f of x exists. And then the third condition is not only is it defined, not only does the limit exist, but they're all equal. So the limit as x goes to c of f of x is equal to f of c. So this one here, at x = -3, what fails? Is it 1, 2, or 3? Well, if we check them one at a time, we usually start here at 1. Is the function defined? And I don't see a filled-in point anywhere. So what is f of -3? So f of -3 is undefined. There's no hole. There's a hole here. It's not filled in anywhere. So I can't give a value for f of -3. So that would be the reason here. What's the type of discontinuity? It would be removable. Removable discontinuity, or you could say point. Okay, the next one here would be x = 2. And we want to look at this point. That's the vertical asymptote at 2. And so the left-hand limit and the right-hand limit are technically equal here. They match, but they don't exist. So let me explain what I mean by that. So remember what I wrote up here. I was a little bit more specific. It says the two-sided limit must exist. And so here the one-sided limits must exist and be equal. So let's check, for example, one of the left limits, or the left or right limit. So 2 from the left of our function here is going to positive infinity. So that's right here, going up to infinity, and this means that the limit does not exist. The one-sided limit. Remember how I was very careful in when teaching these limits. I would say to you that this infinity doesn't mean that the limit exists. It's just more specific than saying d and e. It's saying it doesn't exist, and by the way, it goes to infinity. So here, number 2, well, actually, number 1 fails. So we'll say f of 2 is undefined. It's on a vertical asymptote. And we could even go further and say the limit as x goes to 2 d and e of our function. So d and e. So it really fails. And the last one here, x equals 3. I think I'm maybe doing part 3 and part 2 here, discussing the continuity at each of these values. So I think I'm kind of answering, I'm doing, this here says, why is it discontinuous? And so I was giving the reason, examining the continuity part, but that's fine. So we're doing part 3 and part 2. So what type? I didn't name the type. This would be essential discontinuity, which means that it's a vertical asymptote or infinite discontinuity. You could also say infinite. Okay, and this one over here is, let's see, so at x equals 3, this would be a gap in between them. So is the function defined? And the answer is yes. It's defined right here. And so it passes number 1, but it fails number 2. So we could say the limit as x goes to 3 from the left of our function does not equal the limit as x goes to 3 from the right of our function. So this is a little plus up here. So the left doesn't equal the right. And then this is also an essential discontinuity. And you could just say gap. A gap is another way that you could describe it. Okay, and number 3, we've kind of analyzed the continuity here by saying that this one, f of 3 is undefined, f of negative 3 undefined. Here, f of 2 is undefined. And this one here, the limit as x goes to 3 of f of x does not exist. So this is like the quickest and easiest way that you could answer number 3. So you're just giving which one of the rules, which one of these 3 fails, and that's how you are answering the question. You're saying, hey, it's discontinuous. So each of these 3 points is discontinuous at the x value, and we're giving a more specific reason why it's discontinuous. Part 4 asks us to discuss the continuity at x equal 1 and x equal 4. So here at x equal 1, if you look right here, that's this point. It appears to be defined. It doesn't look like there's a hole, so f of 1 is defined. You could say it looks like it's defined at 3, so f of 1 equal 3. And does the limit exist? So the limit as x goes to 1 of f of x, what does that equal? So the left limit coming from this direction looks like it's getting closer to 3, and the right limit here also looks like it's getting closer to 3. They meet up at that point, so the limit exists and is 3. So this is part 1, this is part 2, and this is part 3. And so we can finally say in part 3, f of 1 is equal to 3, which is also equal to the limit as x goes to 3, goes to 1 of f of x, which is 3. So this continuity statement here is really not necessary. I mean, you could say it, but you could just also observe. You could say, therefore, it's continuous for part 3. So let's do that for part 4, or x equal 4. So x equal 4 is right here. It looks like it's defined at 1. So for part 1, I'm going to say f of 4 it's defined. It's equal to 1. And 2, the limit as x goes to 4 is of f of x is equal to the left side, coming from the left and coming from the right. They both meet up right there at 1. So this is equal to 1. And so we could just say for part 3, therefore, f of x is continuous at x equal 4. Now, the continuity statement, you could say these are, so you could say 1 equals 2 or something like that. I mean, that's the idea that we want to convey. 1 equals 2 there. So I'm saying my circled points, of course, the number 1 doesn't equal 2. But that's the idea that we're trying to convey, is this third part. So you check 1 and 2, make sure that it's defined, the limit exists, and that they're equal, therefore it's continuous. Okay, what do they want down here? Let's give it a read. Determine whether the function whose graph is given is continuous at the values of x. Justify your answer. So here, we want to give, I usually draw some pictures for this and ask you to answer them. So give me one moment while I draw my pictures. I had them drawn on the next page. So I used to draw these by hand. It looks like we actually put them into the notes. So here they are. So let's go ahead and look at them. The instructions, again, were right here. Determine whether the function whose graph is given is continuous at the given x values. Justify your answer. So what are the given x values here? So the first one is -3. That's right here on this graph. And it looks to be a vertical asymptote. So what we're going to do is check case 1. And as soon as one of the 3 cases fails, then we stop. If it passes all of them, then you can say that it's continuous. So what we want to do is say, so let me remind you of all 3 cases. First case is f of the value, the x value is defined. So we'll just say is defined. That's the first one. I'll usually call that 1. And 2, the limit as x goes to c of f of x exists. And part 3 is not only is it defined, and not only does the limit exist, but they actually meet up at the same place. Okay, so this you really want to have memorized, and what I'm going to write above this is just continuity. So this is what it means for to be continuous. It's defined, limit exists, and it connects. So here, we want to check f of -3. This is undefined, because it's on a vertical asymptote. So this is discontinuous. F is discontinuous at x equal -3, and we'll just put in parentheses here, infinite. It's infinite discontinuity because we're in a vertical asymptote. At -4, that's right here. Let's do this one in blue as well. Blue. We're going to have part 1, f of -4. It looks to be -1. Part 2 is the limit as x goes to -4 of our function. Notice that the left-hand side and the right-hand side appear to connect at the same point. So that's going to be -1. And so part 3 will say f of -4 equals the limit as x goes to -4. And then we can say, therefore, f is continuous at x equal -4. It's a lot of writing, it's a lot of work, but that's the idea. And so we're doing the same thing for each x value. Maybe we'll remove one of these so that we're not redundant here. So let's see, -2, -4, and let's try 2. So let's get rid of -4 here, and we'll just do 2 and -2. So here's -2. F of -2 is defined. It's right here at 1, so it passes 1. Let's check 2. The limit as x goes to -2 of our function. Here's the left limit. Here's the right limit. Notice that they don't meet up. The left limit is 1. The right limit is -2. So this D and E This limit does not exist, and we could give a little reason. We could say the limit as x goes to -2 from the left, that's going to be equal to 1, is not equal to the limit as x goes to -2 from the right of our function, which is -2. And so then we could say, therefore, f is discontinuous at x equal -2, and we'll give a type of discontinuity in parentheses. In this case, it's a gap. This is essential discontinuity. Okay, let's try 2 right here. It's defined, so 1, f of 2 is 2. 2, the limit as x goes to 2 of our function exists. The left side meets up with the right side, so that's also 2. And so then part 3, we could say the defined value is equal to the limit value. So where the limit is equal to the function value. So this is f of x. And so we could say, therefore, f is continuous at x equal 2. Now, this isn't really a proof of continuity or discontinuity. It's more of a verification. We're checking the conditions, and we're seeing that the conditions are met. Therefore, we're saying it's continuous. Proof of continuity at all points in the function would take a little bit more effort than what we're able to do at this point. So this will have to be good enough for us. Okay, on the next page here, I think we're doing more of the same, but this time they're giving us a function in terms, a defined function instead of a graph. So here we're going to have to be a little bit more intimate with the rules instead of just looking at a graph and saying this is the left limit and this is the right limit. So let's go ahead and jump right in. So they want us to first check each one of the conditions. So what is f of 1? Well, notice that the rule 1 goes to the top piece. This is greater than or equal to, or less than or equal to, so it goes to the top piece. So this is going to be -1 plus 4 or 3. So it's defined. Now let's check the limits. So I'm immediately going to go to the left and right limits. So the limit as x goes to 1 from the left of our function. The left of 1, let's see, is here. The top piece, that's less than 1, so we're going to have -x plus 4. So that's going to be plugging in there. We're going to get -1 plus 4 or 3. Okay, now let's check the right of our function. So it's probably more appropriate to put f here and then replace the appropriate piece of the function. So the appropriate piece would be this side. This is the right. So we're going to have the square root of x minus 1. And then if we plug in 1 here, we're going to get 0. So notice the left hand and right hand don't meet up. So we're going to say the limit as x goes to 1 of our function does not exist, unfortunately. So what does this mean? This implies, or you could say therefore, f is discontinuous at x equal 1, and the type of discontinuity, since the left-hand side goes to 3 and the right-hand side goes to 0, it looks something like this. So that would be a gap or essential. So if you said essential or gap, those would both be acceptable. Okay, let's try at 4 here. So notice at x equal 1, that's where the rule changes. So there is a greater risk of discontinuity at the rule change. So here at x equal 4, I expect, or at least I hope, this is going to be continuous. So let's check. F of 4. 4 is greater than 1, so it gets sent to this one. That's square root of 4 minus 1, or the square root of 3. Part 2 is the limit as x goes to 4 of our function, f. Well, what is left of 4? Well, maybe something like 3 or 3.9. And 3.9 is greater than 1, so it's still in the square root. Well, what's right of 4? Maybe something like 4.1. Well, 4.1 is still greater than 1, so it goes to the square root as well. So this is just both left and right hand sides of our limit are going to go to the square root of x minus 1. So this is going to be square root of 3. So for part 3, we see that our function f of 4 is equal to the limit as x goes to 4. So we can say, therefore, f is continuous at the x value, x equal 4. Yeah, all right. Let's check this one over here. Part 1, f of negative 3. We want to plug in negative 3, and we're going to get 9 plus 3 minus 6. Is that right? Yeah. Which is going to be something, 6. And in the denominator, we're going to have negative 3 plus 3, or 0. So this is undefined. I like that because we're done. So this implies f is discontinuous at x equal negative 3. And the type of discontinuity is because it's undefined, and notice what we are getting here. We have a number over 0, and just like our limits, that implies we're on a vertical asymptote. So this is going to be infinite. Okay, I hear my baby crying, so I will go tend to her real quick, and I'll resume the video in a moment. Okay, we'll now do the same here for number 8. Let's give it a try. So first we want f of 6. It's going to be 36 plus 6 minus 6 is 36. And part 2, the limit as x goes to 6 of our function. And it turns out if you just plug it in, 36 over 6 plus 3, which is 9. So 36 over 9 is 4. And so it turns out if you just plug in the value, 36 over 9, you're going to get the same value. So remember, when you take a limit, you have to plug in, you try to plug in the value. And here, if we just plug in 6, we get a number. So that is our limit. So for part 3, our function is equal to the limit value, which we could say, therefore, f is continuous at x equal 6. Here it says find where the function is discontinuous and discuss the discontinuity. Well, usually discontinuity happens wherever there are problems in the domain. So what I'll do here is I'll say something like look for domain issues. So find domain. We could say issues, or domain issues, or domain gaps, or gaps. So in this case, this one here, we're going to have a vertical asymptote at x equal 3. So by setting the denominator equal to 0, we know that x equal 3 is not in the domain of the function, because we're going to get 0 in the denominator. So let's first write x equal 3. And this is going to be a vertical asymptote, so that means that the type is infinite. And then y, we could say f of 3 is undefined. So it doesn't pass the first step. Let's try the same thing on this one here. So I would suspect that where the rule changes is where there's going to be a discontinuity. So let's kind of observe there. If I try to plug in 1 here, what do we get? We're going to get 0 over 0. And if we try to plug in 1 here, we get 1. So what we want to know is where does the function meet up where it's defined? So what is f of 1? So we're considering x equal 1 at this moment. What is f of 1? Well, f of 1, since x is equal to 1, goes to 1. Well, then what is the limit? So it's defined. What is the limit as x goes to 1? Well, the left-hand and right-hand sides are both on this function. Because if you're left of 1, that's not 1, so you go here. And if you're right of 1, that's not equal to 1. That goes here. So both cases, left and right of 1, go to this x squared plus 3x minus 4 all over x minus 1. And we can factor the numerator. So let's go ahead and do that. X maybe plus 4x minus 1. And the x minus 1 factor is removable, so it goes away. And so we have the limit as x goes to 1 of x plus 4. And then we can just plug in the 1, which is just going to be 1 plus 4, or 5. So here, we want to say f of 1 does not equal the limit as x goes to 1 of our function, which was 5. This is 5, and we saw that this is 1. So what type is this? Well, we've learned earlier in the year and during this distance learning portion that this implies that there's a hole. So this would be a point or removable point. You could also say removable. So over here you could have also said essential. Yeah, so we're going to do the same thing with these here. Discontinuities with this function. Well, so this one's domain is defined for all real values. So domain, you have to try to think of things that make it undefined. So is it possible for me to make the absolute value undefined? And the answer is no. This function is defined for all real numbers. So if it's defined for all real numbers, then are there any breaks in the function? Well, I can make a quick sketch of this function. It's shifted to the right by 1 and shifted up 3. And it's a V shape. So right here is the V. And this 2 out in front is a stretch vertically. So this is what the graph looks like. And we see no. So can I draw this whole graph without picking up my pencil? And the answer is yes. And so here we're going to say no discontinuities. So the fact that the domain is all real numbers doesn't imply no discontinuities. You can have a function that's defined for all real values and still have many discontinuities. What gives us the fact that what gives us that it's continuous is that the function is connected at every point. So it's defined at every point and it's connected at every point. So here, in order to find number 12's discontinuities, let's perhaps factor the function first. So in the numerator we're going to have x minus 3 and x plus 3. In the denominator, we're going to have an x minus 3 and an x plus 2. And so now we can check f of maybe 2 and -2 and 3. So the two places that we're interested in, there's going to be 2 of them here. So let's check 3 and -2. Now, why did I choose both of those? Well, if you look at the denominator here, the denominator will be undefined, or the function's not going to be defined if x is one of these 2. And so you could immediately go ahead and say here, for this part, it's going to be a discontinuity because f of 3 is undefined. And here, this one's going to be f of -2 is undefined. But they're going to have different types, so that's what we're interested in finding. So the reason that these are undefined is because we're going to get either 0 over 0 or a number over 0. So let's go ahead and plug in 3 and see what we get. This one, if we plug in 3 here and here, we're going to get 0 over 0 times 6 times 5. So that's 0 over 0. Now remember, when you have 0 over 0 like this, that's and you can cancel, that implies a hole. So this here would give me a hole. So this is a point or removable discontinuity. And for x equal -2, if we try to plug that in, we're going to get -5 times 1 all over negative 5 times 0, which is negative 5 over 0. So this is, we recognize that anytime you have a number over 0 that's undefined and implies you're on a vertical asymptote. So this would be infinite, or you could say essential. Yeah? How are we doing on time? Okay, doing okay. I'd like to try to wrap it up here. Well, I think that's actually all I had. I was thinking that I had more examples. I shortened the notes so that we could fit it into these times, and it looks like I had plenty of time here. I did try to speed it up there at the end of the video because I couldn't remember how many examples I removed, but it looks like I removed enough. So what we'll do in class this week is we will look at worksheet 6 together. So make sure that you're attempting that, and I will open up Math Space Unit 9, Day 6. So try to get those done for class this coming Tuesday and Thursday, and this is our last week. This is week 8, so this is it. So thank you for watching, you guys, and I will see you guys in class under 40.